Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is an extension of trigonometry for the trig or pre-calculus student, honestly. And it is a delving into what we call the polar coordinate system. And this is usually a pretty big topic in Calc 2. And it's covered a little bit in trig and a little bit in pre-cal, at least at our college, even though honestly in a true trigonometry course you would delve as deeply as you could into this topic. It's a really cool topic. So let's start talking about a new coordinate system altogether. Right now, all you really have dealt with up to this point in mathematics is the Cartesian coordinate system. And that would be this guy right here, the XY axis. And it's probably one of the most logical coordinate systems you could develop. You go over so many units and up so many units, and you arrive at a point, in this case 2, 3. However, that's not the only way to arrive at that point in space, as long as we all would agree that there is a center to space. So if you have a center that you're willing to call the center, for example, in this case with the Cartesian coordinate system, we call that center the origin, then from there you can judge the distance to other points in that coordinate system using some special measure that you've created. And like I said, in this case, it's just going over to the right or to the left so many units and up or down so many units. So this is kind of what New York City is based upon. If you've ever seen or been to New York City, the streets, for the most part, are a grid. And that grid system is the Cartesian coordinate system. Go over 3 avenues and up 3 streets. But that need not be the only way that you measure out how to get to things. And one of the most popular alternative coordinate systems in mathematics is called the polar coordinate system, which is what you're kind of seeing here. Although this one is measured in degrees, just because the paper that I'm using, most of us would measure things not in degrees, but instead in radians. But the whole point is you still pick a center to your universe. Let's get right here. In this case, in the polar coordinate system, we would not call that the origin. We would call that the pole of this polar coordinate system. And instead of going over to the right or to the left so many units and up or down so many units, instead we'd start by facing what we call the polar axis. And that's this guy right here. It's just what we would normally consider to be the positive x-axis. So in polar coordinates, honestly, you only have 1/2 of an axis. It's a single ray emanating out from the pole, and that's the polar axis. And then to get to a point, just like we went to 2, 3 in the Cartesian coordinate system, to get to a point in the polar coordinate system, you would start by facing that polar axis, and then technically the way the points are listed is that you would go out so many units. Let's say we went forward 1, 2, 3, 4 units, and then you'd rotate through an angle. So you'd go through an angle of, let's just say, 30 degrees. So you rotate through an angle of 30 degrees to arrive at that point right there. And the way you would label that point is how far out you stepped. And so we stepped forward 4 units, and the angle through which you turned, 30 degrees. And that would be called R, and this angle would be called theta. Now, honestly, when I plot a point in the polar coordinate system, I don't go forward 4 units and then turn through an angle of 30 degrees. I go backwards. I go and turn through an angle first and then step forward. For example, If I said that we want to plot the point at 150 degrees, which is way over here, if we want the point that is at 150 degrees and maybe 3 steps out, I would first say stand at the pole and face the polar axis here, and then turn through an angle of 150 degrees. I'm curious if that's 150 degrees, so let me just double check. It is. Great. So you turn through 100, so you start by facing this direction, turn through 150 degrees. There we are, it's 150 degree turn. And then step forward 2 units. 1, 2. So that point is 2, 150 degrees. And likewise, you could turn forward or backward all day long. It actually does not matter. You could have positive angles, negative angles. Your step size even could be negative. So let's go ahead and at least get the official definition down. Then we'll take some examples to really solidify the mindset. So here's the, well, I shouldn't say official definition, but it's pretty much close. This is the definition that I wrote. In the polar coordinate system, the point considered the center of the system, usually called the origin in the Cartesian coordinate system, is called the pole, which I've just said in a previous page. The horizontal ray emanating from the pole and progressing to the right is called the polar axis. That would normally be our positive x-axis. With these two definitions set, the polar coordinate of a point P in the polar coordinate system is defined to be the ordered pair P, which we normally don't write the P next to it, but I wrote that there because we're talking about a point named P, so I just wrote P next to it. But it's r comma theta, where r is the distance from the pole to the point P, and theta is the angle from the polar axis to the ray terminating at the point P. Again, I just want to mention that r can be negative and theta can be negative. So let me write that down. Now what we're going to do is actually take some examples here, and we're going to I was going to say we're going to freehand some of these, but actually I think initially let's go ahead and plot things on a actual polar grid paper. Let's start by plotting these points, and we could always add more if we want to. Maybe there's something we've forgotten here or whatever, but we'll start with this number 1 and we'll check these off as we go through. And hopefully, like I said, it covers all cases. So starting with 2 comma pi over 3, I'm going to zoom out here. And 2 comma pi over 3. Well, notice this specific piece of graph paper here has everything listed in, unfortunately, degrees. So we know that 60 degrees is the same as pi over 3. So to plot 2 comma pi over 3, we start at the pole here, and we'll rotate through an angle of pi over 3 first. That's how I usually do it. So I start at the pole and face the polar axis there, and I rotate through an angle of pi over 3. That angle right there is a pi over 3. Sorry, I'm using a different ink here because the resolution of this screen is crazy high. So pi over 3 right there. And then once I'm facing that direction, I will step forward 2 units. And in this case, the units are these concentric circles. So there's step 1 and step size of 2. So this point right here is the point 2 comma pi over 3 in the polar coordinate system. Now I hope it makes sense that you can actually land anywhere on this 2-dimensional grid using the polar coordinate system. So you could use either the Cartesian or the polar coordinate system to land anywhere in 2-dimensional space. And in fact, the polar coordinate system, just like the Cartesian coordinate system is very much like New York City, the polar coordinate system is very much like Amsterdam. Amsterdam has a center, and then all of the streets emanate out in like this raised style of pattern from the center. It's just another way a city can be laid out. Anyhow, let's go ahead and see what our second point to plot would be. So we already plotted 2 comma pi over 3. Let's go ahead and plot 6 comma 5 pi over 4. 6 comma 5 pi over 4 means that I'm going to start by facing the polar axis here. So that's this big black ray going out. And we're going to turn through an angle of 5 pi over 4. Now, that would terminate in quadrant 3. So remember, we rotate out to there. That's an angle of pi, or 4 pi over 4. 5 pi over 4 is actually right there. They don't actually plot it here. And also, I just noticed they actually label angles negative in this direction. Kind of interesting. So if that's 180, this is 190 degrees. This is 200 degrees. This is 210 degrees, which I'm going to remove that out. This is 220 degrees. This is 230 degrees. But halfway between those two is 225 degrees, which is 5 pi over 4. So I'll first rotate through an angle of 5 pi over 4 here, which is roughly about here. And then I'll look forward. There's 1 step away. We want to get 6 steps away here. So it's 1. There's 2 steps. Here's 3 steps. 4 steps. 5. And then 6. So this point right here is 6. And actually, I will use a different ink for that. 6 comma 5 pi over 4. Now, honestly, when I'm graphing, I don't use graph paper, so it's technically a little bit easier without graph paper like this, I think. It's just much easier. Also notice that I did not draw out, like we have been up to this point in our trig course, I did not draw out a line emanating from the center. We have been doing that throughout trig, so I think most people would initially do this. Oh, look, I have this line. But you technically do not have a ray here. These are just points plotting in space. So there are no rays or lines that you're really worried about. But you could do that. There's nothing wrong with doing that. It's just most people would not. All right, let's take a look at the next point in line. So that was 6 comma 5 pi over 4. Let's look at negative 6 comma pi over 4. So this is the first time we're considering a negative distance away from the pole. A negative radius is what I'd call that. That's why it's called r, because it's a radius. So the negative radius. Let's see, we want to plot, again, negative 6 comma pi over 4. So the first thing I'm going to do is rotate through an angle of pi over 4. So that would not be here, because that's 30 degrees. That would not terminate there, because that's 60 degrees, but it'd be halfway through that. So I'd rotate to this angle right here, which is actually a pi over 4 angle. I'm facing that direction. However, the negative 6, which is our radius, means that we're going to step backwards. So we're facing this direction right here, and we're going to step backwards 1, 2, 3, 4. Looks kind of weird when I'm doing this. 4, 5, and 6 steps. Again, to convince you that I'm doing that correctly, we know that pi over 4 is a 45 degree angle. So we're facing this direction right here. And we are now going to step backwards 1, 2, 3, 4, 5, and 6 steps. So right to here. And notice this point we had already labeled as 6 comma 5 pi over 4, but it's actually the same thing as negative 6 comma pi over 4, which brings into play the fact that polar points have an infinite number of representations, because you can get to that point by facing the opposite direction and stepping backwards, or technically you can get to this point by going to 5 pi over 4 and adding 2 pi. In other words, I could say don't go to 5 pi over 4. Instead, go to 5 pi over 4 plus 2 pi, which is 13 pi over 4. Let me just double check that that's right. Yes, it is. And then step forward 6 units. So we see already 3 representations for that point in space. In fact, let's leave that pi over 4 there for the time being. In fact, the next one, 6 comma negative 3 pi over 4, says go ahead, face the polar axis. So we'll start by facing the polar axis here. Let me erase all my handiwork. So we're facing this polar axis, the black ray that's emanating out, and we'll rotate through an angle of not positive, but negative 3 pi over 4. Negative 3 pi over 4 would rotate all the way back to here. That is a negative 3 pi over 4. So that's the direction that we're facing now. We're facing this direction. And then we'll step forward 1, 2, 3, 4, 5. Am I even on? Yeah, I am. 6 units. There we go. And so yet another representation for that point, 6 comma negative 3 pi over 4. Just remember, it's in alphabetical order the points are. It's r comma theta, T-H-E-T-A. R theta. So don't write them backwards. It's very easy to write them backwards the way that I plot these points, because I always turn through the angle first. And so it's incredibly easy to just plot them or state the numbers the wrong way. But the correct order is r comma theta. All right, I don't need that ruler anymore, because the last few points we're going to plot here, at least on this constrained polar axis, in other words, the one where somebody's given us a curve or a piece of paper. The rest of them we don't need a set ruler. So let's plot 2 comma 0. That means face the angle of 0 and step forward 2 units. Well, if you're facing the polar axis, then you're facing the angle of 0. Stepping forward 2 units, you would land right there. That point is 2 comma 0, which actually aligns with what we would call it in the Cartesian coordinate system. Don't get used to that. It just happens to be the case on the polar axis. All right, let's take a look at another point. We're almost done with these, and then I'm going to go to freehand drawing, which is much easier, I think. And then 2 comma pi is what we're going to graph. So we'll turn through an angle of pi. Pi being 180 degrees, so we just rotate through an angle of 180 degrees and step forward 2 units to this point right here. And we'll label that 2 comma pi. Now it looks weird because you're on the what you would consider to be the negative x-axis, so it looks really weird that first coordinate is positive, but it's positive because that's the radius. You turn through an angle of pi and step forward from that center 2 units. So that's the way you should think about working with polar coordinate system, is stepping forward, stepping backward from a center. Finally, let's go ahead and plot -1 comma 3 pi over 2. Again, you start by facing the angle, which is 3 pi over 2. So I'll rotate through an angle of 3 pi over 2, which lands us right here at 270 degrees. That's 3 pi over 2. And then, now that we're facing that direction, we will actually step backwards because we want to plot -1 comma 3 pi over 2. We'll step backwards to here. 1 step. That is -1 comma 3 pi over 2. So there, we've gone through all of those examples. Now, in reality, if you're asked to plot a point in the polar coordinate system, normally you're not handed a piece of paper to do that. So how would you do that? Well, if I asked you, let's say, to plot -2 comma 7 pi over 6, let's just say that's the point right there, I would start by just putting a point in space. I would also go ahead and draw the polar axis. Then I would probably, for me in a different color, turn through an angle of 7 pi over 6. That's 6 pi over 6. And 7 pi over 6 means you're facing technically this direction. Well, maybe that's a little too far, but it doesn't really matter. You're facing like this direction right here. That's about 7 pi over 6. Okay, so we've rotated through that angle of 7 pi over 6. We're facing that blue arrow direction right there. Yet we're going to step backwards 2 points. So I will go ahead, maybe go back to black ink here, and I will step backwards 1. Whoops, that was not supposed to be like that. Step backward 1, 2 points. So this point right here is -2, comma 7 pi over 6. So it's a really not too bad, and to draw these out very quickly, even if you're freehanding it. It looks weird because it looks just like you have an arrow in space, but that's really the polar coordinate system. There's not much to it. If I asked you to invent other points that were similar to this, which I think is what we're going to be doing next, then you could totally do that. This point is actually the same as having turned through an angle of regular old pi over 6 and step forward 2 units. So there you go. So just remember, unlike the Cartesian coordinate system, a point in the polar coordinate system has an infinite number of representations. And that ends up being kind of weird for us because we do not have like a one-to-one correspondence between a point in the Cartesian coordinate system and a point in the polar coordinate system. If somebody hands me the point 1, 1 in Cartesians, I know there's a point in the polar coordinate system for that, but there's actually an infinite number of points. The other way around, though, a point in the polar coordinate system only goes to 1 point in the Cartesian coordinate system, and it's because points in the Cartesian coordinate system only have one representation, right? 1, 1. That's just it. So, but in the polar coordinate system, we could say, well, that distance right there, if you told me the x value was 1 and the y value is 1, I could use Pythagorean theorem and tell you that distance is √2. So in the polar coordinate system, I could get to that point by turning through an angle of pi over 4 and stepping forward a √2 units. Or I could, for example, go backwards through an angle 3 pi over 4. If I do that, though, to get to this point, because I'm facing the wrong direction, I would step backwards a √2 units. So there are many ways, starting from a Cartesian point, to get to a polar point. But if I told you I just have this point in polars right here, to √2 comma pi over 4, there's only one such representation in Cartesians. Interesting little side note there. Just to wrap up the point plotting process and all that stuff, let's go ahead and just do an official example. Give 3 other ordered pairs for the polar coordinate 2 comma pi over 6. It might, in fact it would be, very helpful to go ahead and plot that point. So here's my pole and polar axis. I'll turn through an angle of pi over 6 and step forward 2 units. There we go. So this point right here is 2 comma pi over 6. Remember, pi over 6 is just a 30-degree angle. If you need to actually draw a line in there, you are more than welcome to. There's nothing wrong with that. It kind of helps in graphing, so I totally understand. But we want 3 other ordered pairs. So just choose how you want to do it. For example, one way I can get to this point is to start at this point and add 2 pi or subtract 2 pi. So let me go ahead and add 2 pi, for example. So I face this point, 2 comma pi over 6, but then I'm going to go ahead and add 2 pi, which is 12 pi over 6. So I end up with 13 pi over 6. That is the same point. Or I could have started at 2 comma pi over 6 and instead subtracted 2 pi. So subtracted 12 pi over 6 and you'd be at a negative 11 pi over 6. Or you could add 4 pi or 10 pi or anything like that. Or you could technically rotate through an angle of, what is that, 5 pi over 6 to face the opposite direction here. And if you're facing 5 pi over 6, you would step backwards 2 units to arrive at that very same point. So imagine you've turned through an angle of negative 5 pi over 6. And so therefore you're facing the equal and opposite direction. To arrive at this point that we're looking at, we would then step backwards. So that would be a -2, -5 pi over 6. Now I've already listed 3 alternative points, but let me just list one more. You could keep going all day long. There's an infinite number of representations, but you could have also said, you know what? I'm going to rotate forward to 7 pi over 6. And then now that I'm facing this blue arrow direction right here, I'll go ahead and step backwards 2 units. So again, backwards 2 units, but you're facing 7 pi over 6. So there are 4 representations right there, but there's actually an infinite number of representations for a point and polar coordinates. I know I've driven that home. I'm just making sure you are well aware. All right, that's it for this video. In the next video, we'll start to talk about how to convert between polar and rectangular coordinates. It's actually not too bad.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.